morning, everyone. I'm Zhixuan from Wuhan University, and I'm delighted to present my research on analysis of monsoon characteristics in China. Firstly, I'd like to talk about my study background. What is a monsoon? When people think of monsoon, don't think of heavy rains that pour down for weeks. Actually, monsoon is an ancient climatological concept derived from an Arabic word, Monsoon, which means season. Now, monsoon is traditionally defined as a seasonal reversing wind accompanied by corresponding changes in precipitation. More than 60% of the world's population live in monsoon-affected areas. These powerful monsoons are the architects of the weather system, bringing intense convective precipitations. Under the background of global warming, we experience increasing extreme weather events, so it's necessary to study monsoon characteristics, learn the monsoon's language to better understand the extreme precipitation events. So how does monsoon work? The land warms up faster than bodies of water, forming low-pressure areas. The moist air blows from above ocean to land, and the water vapor then condenses and becomes rain. In winter, it's basically the opposite. Among all the parameters used for monsoon studies, water vapor is crucial for the formation of precipitation and more directly related to convection, making it favorable to analyze monsoon characteristics. Currently, there are various methods for water vapor acquisition. Compared with the other traditional methods, ground-based GNSS has huge advantages, such as its high accuracy, high resolution, and odd weather condition. With the development of multi-GNSS constellation and the densely distributed GNSS network, the increasing GNSS-based water vapor records will serve as a high-quality data source for monsoon studies. So in this work, we utilize the advantages of GNSS-based water vapor products to analyze the monsoon characteristics in China, mainly including two aspects: the monsoon region determination and the monsoon movement characteristics indication. We selected nearly 1,000 densely distributed GNSS stations in China. The data covered the time period from 2016 to 2020. We can estimate high accuracy Zenith Tropospheric Delay during the GNSS data processing. Well, for precipitable water vapor retrieval, we also need meteorological data. Here, we obtain the station pressure and the water vapor weighted mean temperature from the ERA5 reanalysis data. Combining ZTD and these meteorological parameters, we can calculate hourly PWI products. This may introduce a measure less than 1 millimeter. We first concentrate on the determination of monsoon regions. As we know, monsoon-impacted areas are always accompanied by significant water vapor differences between wet and dry seasons. So the statistical distribution of PWI data may serve as a standard to determine the monsoon regions. Existing research indicates that PWI data generally follow a bimodal distribution in areas with significant seasonal variations. According to this, we tested different schemes and finally selected a bimodal monsoon metric suitable for China. This metric is expressed by ptosis and skewness. Lower values indicate larger bimodality, that is significant influence from the monsoon, while higher values indicate lower bimodality, that is far from the monsoon effect. We selected two representative stations to study the statistical distribution of PWI. The figures show the total histograms, the log normal Physics curves, and the monthly histograms. We can see that for station 1LJ, located in the Monsoon region, the PWI data follows a significant bimodal distribution. That means distinct water vapor variations between wet and dry seasons of the year. While for station GSDH, located in the non-Monsoon region, the PWI data follows a unimodal distribution, and the monthly distribution histograms are also more concentrated. So then we calculated the bimodal Monsoon matrix for all stations in China. The figures show the geographical distributions of the matrix. We can see that the southwestern and the eastern regions of China exhibit strong bimodality. They are respectively affected by the southwest monsoon and the East Asian monsoon, while the northwestern regions, on the other hand, has weaker bimodality and is usually considered as the non-monsoon region. To test whether the monsoon is a decisive factor of the bimodal matrix, we selected May to September as the major monsoon dominating period and excluded this part of data. The bimodality of the remaining parts show a noticeable weakening, so we can think that the bimodal monsoon matrix we selected is effective. For the second part, we come to the monsoon movement characteristics indication. The onset of monsoon is always swift and accompanied by a fast transition between wet and dry conditions. So we can utilize the temporal variations of the PWI to quantify the exact time of the monsoon onset and retreat days at a given location. Here we constructed the normalized precipitable water indexes through normalization in order to eliminate the dependence on location and set a uniform empirical threshold. If the NPWI of 3 consecutive days exceeds or falls below the threshold, the first day is considered as the monsoon onset or retreat date. Here, we selected 3 representative stations in the monsoon regions. The figures show their NPWI time series containing the monsoon onset and retreat days, and the dashed line represents the threshold. We can see that the NPWI, that the monsoon onset and retreat days vary across different stations. To verify the reliability of the NPWI determining monsoon onset, we introduced other meteorological variables here as a reference. To be specific, we generated a 5-year composite plot of geopotential heat and wind field at 700 hectopascals around the monsoon onset days. Generally, the pressure level of 700 hectopascals corresponds to the altitude of about 3 kilometers. That is located in the mid-troposphere. This level gives us a clear picture of the atmospheric circulation patterns. The left-hand graph shows the meteorological conditions 3 days previous to the monsoon onset, while the right-hand graph shows the very day of the monsoon onset. We can see that around the monsoon onset days, there are significant changes in meteorological conditions, such as the noticeable shifts of the pressure centers, the intensification of the wind fields, and the clear changes of the wind directions. So these findings give us confidence that the study method is reasonable. According to the standard mentioned above, we calculated the monsoon onset and retreat days for all stations in China. The colors in the figures represent the day of year. We can easily observe the propagation of the water vapor front. Generally, the monsoon advances from southeast to northwest with an uneven speed. To conclude, in this study, we utilized the advantages of 2016 to 2020 PWI products from nearly 1,000 densely distributed GNSS stations in China to analyze monsoon characteristics. The bimodality of the statistical distribution of PW was employed to measure the monsoon effects across various regions, and normalized precipitable water indexes were constructed to characterize monsoon onset and retreat. That's all. Thank you.